Let's look at an example where we use that gain sensitivity equation to see just how much our feedback can improve our circuit stability. So in this example, we want to calculate our feedback transfer function given A equals 10 to the fifth and AF equals 50. So again, this just highlights how important it is to know our terminology. So feedback transfer function means we're trying to find our beta value, and we're given these two values here. So remember, our A is going to be our open loop gain, and our A sub F is going to be our closed loop gain. So we know from our basic equation, we know that our closed loop gain is equal to A divided by 1 plus beta A. So of course we can just rearrange this to solve for beta. So we can say beta is going to be equal to A divided by AF minus 1, and all of that divided by A. If we plug in our values, we have 10 to the fifth for A, 50 for A sub F, minus 1, and we divide that by 10 to the fifth, and we get that our beta is equal to 0.01999, so 3 nines. And so this would be the answer for the first part. And so this is a pretty typical value of beta. One thing that we can note is that if we had neglected this -1 term, so neglecting our -1, and so I'm referring to this -1 here, what we would have gotten then is our beta equals 0.02. So we can see, of course, that's a pretty good approximation to 0.01999. Alternatively, we could have also said, well, beta A is equal to 0.01999 times 10 to the fifth, and we see that's equal to 1,999, and we can say, well, that's a lot bigger than 1, so we could use that approximate equation, AF equals 1 over beta. Again, it depends on what the situation as far as whether you want more detail or whether you want to save calculation time and get a first order approximation. Okay, so hopefully that's pretty straightforward. Now for the next part of this problem, we're told that our open loop gain is changing by 10%, and what we want to do is calculate the change in our closed loop gain. So again, it's important to know these terms. So our closed loop gain is talking about A sub F, and our open loop gain is talking about our A. So now we're going to go to that equation from our previous video about gain sensitivity. So we had the percent change in our closed loop gain is equal to 1 over 1 plus beta A times the percent change in our open loop gain. And so it's important to note that all of these values here are our original values. So all of our changes, and so let me include this guy too. So all of our changes are sort of encompassed in this DAF and this DA term. So if we plug in the values, including the beta that we just found in the previous part, we have down here in the denominator, we have 1 plus, and now our beta value was, if we use our exact one, 0.01999. Our original A is 10 to the fifth, so all of that divided by 1. And so remember, this value down here, this 1 plus beta A is our desensitivity factor. And we multiply that then by our original A, which is 10 to the fifth. And then we are told that this open loop gain changes by 10%. Well, 10% of 10 to the fifth is 10 to the fourth. So our DA is then going to be 10 to the fourth. So we plug that in, and we get that our DAF with respect to AF is equal to 5 times 10 to the minus fifth, which is equal to only 0.005%. So that's pretty impressive. So we've changed our open loop gain by 10%, and we only saw a 0.005% change in our closed loop gain. So think about what that means in terms of a circuit. So that means we could have an HFE parameter varying by 10% or more, and yet still see these changes in our overall closed loop gain of much less than 1%. So pretty impressive stuff. But on the flip side, the disadvantage of using our feedback network is that we noticed that we had this relatively large gain for our open loop configuration of 10 to the fifth, and when we employ the feedback, that drops down to only 50. So again, like with all of our designs, we're going to have pros and cons and trade-offs that we need to make depending on the application.